Hello everyone, myself is Dr. Vinay Kumar PN. I'm a faculty of mathematics from Sri HDD Government First Grade College, Padavalahipe. Today we are going to discuss about Green's theorem. Green's theorem is a theorem in the mathematics which gives a relation between a line integral of a simple closed curve and the double integral over a region bounded by that simple closed curve. And this theorem has been named after British mathematical physicist George Green. In fact, this theorem has various applications in physics. Then what is the statement of this theorem? This theorem states, suppose C is a positively oriented piecewise smooth simple closed curve in a plane, and if D is the region bounded by this curve C, and if P and Q are functions of x and y, which are defined over D and having continuous partial derivatives on D, then line integral over C p dx plus q dy is same as double integral over D dou q by dou x minus dou p by dou y into dx dy. Since this C is positively oriented, we are writing it in a positively oriented region, plane, and it is piecewise smooth, so there is no crossings, and it is a closed curve, and we have partitioned this curve into 4 parts: C1, C2, C3, C4. All these 4 together will give you C. That is, your C is equal to C1 plus C2 plus C3 plus C4. And D is the region bounded by this curve. And here our x runs from A to B and y runs from xi of x to eta of x. Now let us see the proof of this theorem. See, from this picture, D can be written as, we know that every point on the two-dimensional plane is of the form ordered pair x comma y. So D is collection of all ordered pairs x comma y, where x runs from A to B, that is A less than or equal to x less than or equal to B. This is the domain for x. And y runs from xi of x to eta of x. Now let's consider double integral of dou p by dou y into dx dy over D. We knew that D is the region which is from x running from A to B, x runs from A to B, and y runs from xi of x to eta of x. Y runs from xi of x to eta of x, dou p by dou y into dy by dx. Now, the integral of dou p by dou y into dy, integration and differentiation, they are reverse process of each other. By that, these two will go off. Simply we'll get p, which is a function of x and y. And y runs from xi of x to eta of x. Now apply the upper limit, so that you're going to get p of integral x runs from a to b, p of x comma eta of x minus p of x comma xi of x into d of x. Now let me take out minus sign as common from this, so that minus comes out, and let me send this one to this side, so that we left out with x runs from A to B, p of x comma xi of x minus p of x comma eta of x into dx. Now apply the integration separately for these two, so that this becomes, remember we have sent this minus sign to this side. Now we are left out with plus sign here. So integral x running from A to B, p of x comma xi of x into dx, that is one integral, minus integral x runs from A to B, p of x comma xi of x into dx. Now here, can we change the limit? Limit is from A to B for this integral, second integral. For the first one, we'll keep the same. For the second one, can we change it from A to B to B to A? Yes, there is a property in definite integral which says that you can interchange the limit by taking a minus sign. So if you interchange the limit from A to B to A, we'll get a minus sign. So that minus into minus becomes plus, and the limit becomes integral x runs from B to A, p of x comma eta of x into dx for this second part. This is what we are going to get. For the first one, x runs from a to b, p of x comma z of x into dx, plus for the second one, x runs from b to a, p of x comma eta of x into dx, and the minus sign which was here has been sent to this. Now from the picture, this is, see, first integral was integral from a to b of z of x. This was the curve. Therefore, this is a line integral over C1. And the second one was integral b to a eta of x. That is this curve. Therefore, the second one is the line integral over C2. In the C2, x runs from b to a because orientation is towards this. The first one orientation is towards this. So that means we are getting this. The first one is line integral over C1 of p of x comma y dx, and the second one is line integral over C3 of p of x comma y. Combining these two together, we can write line integral of C1 plus line integral of p of xy over C1 plus C3. Now we should see that the line integral of p of xy over C2, here our x is constant because over this our x is simply b. Therefore dx will be 0. No rate of change of x. So 0 rate of change of x. Similarly, in the C4, the x is constant a. Therefore dx will be simply 0. No rate of change of x. Rate of change is simply 0. There is no change in the rate. Therefore, the line integral over C2 and line integral over C4 of p of x comma y with respect to dx is simply 0. If you add this with 0, you will get 1 C2, 1 C4. Combining all these four, we'll get line integral over C1 plus C2 plus C3 plus C4 of p of x comma y dx. But this is our C. So we are getting minus double integral over d dou p by dou y into dx dy is equal to line integral over C p of x comma y dx. Similarly, you can show that double integral of dou q by dou x into dx by dy over d is also equal to this, which is nothing but line integral of q of xy dy over C. Combining these two, that is adding these two, in the left hand side you will get double integral over d dou q by dou x into dx dy minus double integral over d dou p by dou y into dx dy is equal to sum of these two. But since both of them are with respect to x and y and over the same region d, we can combine these two and we can write this one as dou q by dou x minus dou p by dou y into dx dy. Similarly here over the same line integral, therefore we can combine this line integral over C p dx plus q dy. This is our actual proof. This is what we need to prove. So this completes Green's theorem. Now let's solve a problem on this. Verify Green's theorem for the function p is equal to xy plus y square and q is equal to x square over the closed curve C, which is covering the region bounded by the curves y equal to x square and y equal to x. Now they are given p and q, so let us partially differentiate this. Partially differentiate p with respect to y, so that you are going to get, when you are partially differentiating with respect to y, your x should be treated as constant. So here x remains same. The derivative of y with respect to y is 1 plus derivative of y square is 2y. And partial derivative of q with respect to x is 2x. Now, they are given D is a region. Now we'll make the partition of the simple closed curve C into C1 and C2. D is the region bounded by the curve C, which is equal to C1 plus C2 as shown in the figure. Then the region D can be characterized as, see from this picture, you can see this is our region D, which is covered by C1 and C2. in between this is our D. So we know that any point on the two-dimensional plane must be an ordered pair. So it is of the form ordered pair x comma y, where x runs from 0 to 1 and y runs from this curve to this curve. This curve is y equal to x square and this curve is y equal to x. And you have to see the orientation. This is towards this and exactly opposite to this is your C2. Now this is what your D. Now we know that Green's theorem says line integral of p dx plus q dy over c is same as double integral of dou q by dou x minus dou p by dou y into dx dy over D. Let us verify the Green's theorem. Now let us find the line integral p dx plus q dy over c, but we have made c into c1 plus c2. Therefore, finding the line integral over c is same as finding the line integral over c1 plus line integral of p dx plus q dy over c2. They are one and the same. So we'll find these two first and we'll submit. Now, first let us find out what is line integral of p dx plus q dy over c1. Now first, from the figure, let us see what is your c1. See, along the curve c1, your x runs from 0 to 1 and c1, which is a curve y equal to x square. So you know that in the case of line integral we have to convert one of the variable into the other so that we can straight away apply the ordinary definite integral method. Now what is your y? Your y is equal to x square. Therefore dy will be equal to 2x into dx. So we can replace variable y by x square and dy by 2x into dx. When you are replacing it, we have to get the limit for the variable x. Here x runs from 0 to 1. Now what happens to your line integral p dx plus q dy over c1? They had given p is xy plus y square into dx and q is x square into dy. But we know that our y is x square. Substitute here. So you will get x into x square plus x square whole square into dx plus x square into your dy is 2x into dx. Simplify this, then you are going to get x, the integral x running from 0 to 1, 3x cube plus x to the power of 4. 1x cube plus 2x cube is 3x cube plus this. Now integrate this one with respect to x. The integral of x cube is x to the power of 4 by 4 plus integral of x to the power of 4 is x to the power of 5 by 5 and apply the limit. If you apply the upper limit, you will get 3 by 4 plus 4 by 1 by 5 minus, if you apply the lower limit, 0 by 4 plus 0 by 5. So this is simply 3 by 4 plus 1 by 5, which gives you 19 by 20. This is the value of line integral p dx plus q dy over c1. Now similarly, let us find along the curve c2. Now along the curve c2, you should note that your x run, see, you have to see the orientation. It is coming from this side. So your x runs from 1 to 0 and on this curve your y is equal to x. When y equal to x, your dy is same as dx. Now we can replace variable y by x. Now let's see what happens to your line integral p dx plus q dy over c2. This is our p is xy plus y square into dx plus q is x square into dy. If you replace y by x, we are going to get x into x plus y is x square into dx plus x square into our dy is dx. And the limit is from x varying from 1 to 0. X varies from 1 to 0 from this picture. Now if you simplify that, then you are going to get the integral x varying from 1 to 0, 3x square into dx. And the integral of x square is x cube by 3. 3 get cancelled. Simply you are going to get x cube. If you apply the upper limit 0 minus lower limit 1 cube, which gives you minus 1. And we know that the line integral of p dx plus q dy, this should be p dx plus q dy, over c is line integral of p dx plus q dy over c1 plus line integral of p dx plus q dy over c2. Sum of these two will give you minus 1 by 20. That is our line integral over c p dx plus q dy. Now let's compute the double integral. Double integral over d dou q by dou x minus dou p by dou y into dx dy, which is equal to double integral of d. We know that dou q by dou x is 2x minus dou p by dou y is x plus 2y. If you simplify this, then you will get double integral over d x minus 2y dx dy. What is our d? D is the region where from the figure x varies from 0 to 1. You can see here x varies from 0 to 1, y varies from this curve, which is y equal to x square, to this curve y equal to x. So this becomes straight away double integral x varying from 0 to 1, y varying from x square to x, x minus 2y. Now first let us differentiate this integrate this with respect to y. When you are integrating with respect to y, your x is treated as constant. So x is constant, integral of 1 is y, minus 2 remains same, integral of y is y square by 2. Dx will remain same, and the limit is from x square to x. 2 get cancels. Now apply the upper limit. If you give upper limit, x into x minus x square minus lower limit x into x square minus of x square whole square. You don't have to give limit again once when they are given with respect to dx. Now this is x square minus x square, which gives 0. This is x cube minus x square whole square is x to the power of 4. If you multiply this by minus sign, that becomes x to the power of 4 minus x cube with respect to dx. Now integrate this with respect to dx, so that this becomes x to the power of 5 by 5 minus x to the power of 4 by 4, and the limit is from 0 to 1. If you apply the limit, upper limit 1 by 5 minus 1 by 4 minus 0. If you simplify this, then you are going to get minus 1 by 20. So we got the line integral of p dx plus q dy over c is also minus 1 by 20. And this one is also minus 1 by 20. Therefore, Green's theorem is verified. In this fashion, we can verify the Green's theorem. I've given certain examples. You can work it out and you can verify and understand the Green's theorem. Thank you.